back in pre-calculus, one of our main concerns was to find the zeros of polynomial functions, and more generally the zeros of other functions as well. Now, those zeros manifest themselves as x-intercepts on graphs. So graphically, we're looking for the x-intercept of, let's say, a graph like this. Now, one of the techniques that was discussed when we couldn't find those zeros easily by factoring and other methods, we a lot of times would resort to a kind of a hands-on method of bisecting intervals. For example, if we're looking here and we notice that we can calculate f of a, and f of a turns out to be negative, and f of b turns out to be positive, then we know by the intermediate value theorem that since we have a continuous function here, that we have a crossing in the interval between a and b. Now, this interval, incidentally, this might be an explosion of an interval that might be really tiny. You see a really tight interval here. But anyway, this may be a magnification of that, but it's the idea that if f of one end of the interval is negative and f of the other end is positive, then there is a crossing within the interval. And one way to get at that crossing point is to use the method of bisection. And I was thinking about the middle point between a and b. It would be a plus b over 2. So we would find that midpoint. Let's say it's right here. So this is the point a plus b over 2. And we would take f of that point, and we would find that it's positive. And we know that f of this left side endpoint is negative, so now we have another interval in which we can work. And so we'll bisect that interval, and we'll maybe select this point, and it would be this plus that over 2. And then f of that point turns out to be down here. And now we have another interval with which to work, and we bisect that interval. You see how the routine is going? Now, each time we go through this bisection idea, that's an iteration of the main theme of this situation. And by doing this again and again and again, pretty soon we get real close to an x-intercept. We can get as much accuracy as we want to with that x-intercept. Well, now, with the calculus methods that we have, we're going to talk about another way to get at the x-intercept. And it's a way that gets at that intercept much faster than the bisection method. It's called Newton's method. And it's based upon this idea, this fundamental concept, that if we have the situation like we have here, f of a negative, f of b positive, then we know by the intermediate value theorem we have a crossing in between those points or within that interval. Then we can do this. We can select any point we'd like within the interval. Maybe we'll take the midpoint. It doesn't really make too much difference. But let's say we select this point as a point to begin with. Now, we take that beginning point and we find f of that point. All right, f of this point would be here. Now, instead of thinking about the bisection of another interval, what we'll do is, instead of the bisection being the next guess as to where the crossing is, we'll make the next guess like this. We'll say, all right, let's take our tangent line at this point and its equation, and from the equation of the tangent line, we can decide on, or we can figure out, we can calculate where that tangent line crosses the x-axis, where it crosses the x-axis. And that is our next guess. And f of that point is down here, and then we have a tangent line at this point, and then the place where that tangent line crosses the x-axis is right in here, and that'll be our next guess, you see. And performing iterations like that, we get at the crossing, or a very good approximation of that zero, much quicker than we would by the bisection method. Now, let's talk about the algebra that goes into this. And we want to talk about a routine by which we can make the calculation sort of by hand. And then I'm going to show you a way to make the calculation a little faster by using the calculator. But we want to know how to do it by hand first. Now here's what would have to happen to go through this idea, and the concept of Newton's method is rather important to us. Consider a function, and this is the function, and for this function f of 0 is -1 and f of 1 is 1. So we know there's a crossing between 0 and 1. We'd like to be able to find it. We're going to use Newton's method. Now here's how we would begin that process. We would find f of 0.5. F of 0.5. Here's 0.5. F of 0.5 is right here. Okay, good. F of 0.5 is this, -0.46. Okay, that's that point. Now, we want to find the derivative, and the derivative is 5x to the 4th plus 1. You see, we want the slope of the tangent line at that point. The slope of the tangent line at this point, that is what we're looking for. So we find the derivative. Here's the derivative. And then f prime at 0.5 is 1.3125. Okay, that's the slope of the tangent line at that point. Now with that slope and with the coordinates of the point, we can actually construct the equation for that tangent line. And that equation then would be built upon this idea. It's y minus y1 equals m times x minus x1. Remember, it was the point slope form of the slope formula. Anyway, we have, let's see, the y component here is this value. The slope is this value. And the x was the x that we chose, that 0.5. That x of 1 is the 0.5 that we chose to begin with. All right, so this now is the equation for the tangent line. Now, in order for us to take this equation and find the x-intercept for the graph of this line, all we do to find that x-intercept is let y be 0. So letting y take on the value 0 and solving this for x, we would find x to be approximately this value, 0.8571. Now, graphically, here's what we're doing. We're saying, okay, we've got a tangent line at this point, and that tangent line has an x-intercept associated with it, and the x-intercept is right here. So this is our next guess, our approximation for the 0, and then we start the process all again. So this is our next approximation. Here we go with the next part of the iteration. It's f of that point is approximately this. F prime of that point is approximately this. That's the slope of that tangent line at that point. Then we go through the y minus y1 m times x minus x1. The y1 is the 0.32. The slope we found by the f prime business. And then x minus x1, the x1 was the value that we chose as our approximation. Okay, and on we go. And we would continue that process. There must be an easier way. You see, I mean, to do this again and again and again, we're doing the same thing over and over again, so there must be a way for us to streamline it, and certainly there is. We want to investigate now generally what's going on with this. As we choose an x, we chose a specific x here. As we choose a general x, what is happening symbolically? What's going on? Well, given an x, and I'll subscript it 1, x of 1, we can calculate f of x of 1. That's that y value, you see. Okay, then using the idea of the point slope form, the y1, you see, is this f of x1. The slope is the f prime of that value, or f prime of x1. And then this is just x minus x1. Now, I'm going to go through and solve this for x, assuming now that I'm looking for an x-intercept, and the x-intercept implies that y takes on the value 0. So the y goes out, and now I'm solving this for x. So I'll take this coefficient and divide it on both sides, giving me this on the left and this binomial on the right. Then I'll add x1 on both sides, and I have this. So the next x that I'm choosing can be found every time by doing this. Now, I might call this the second x because I chose the x of 1 is the first x that I chose, and x2 I'm calculating this way. And even more generally than that, the n plus 1th x that we're choosing in multiple iterations will be the previous x minus this fraction. And that's basically the fraction that we have right here in terms of x subscript n. Okay, now with this idea, we can make a chart that will allow us to calculate this value, or the value for this next x, by in the chart just going from one step to the next. We need this calculation. We need the calculation of x sub n. We need the calculation of f of x sub n. We need the calculation of f prime of x sub n. We need the calculation for this fraction, and then we can easily get the calculation for x sub n plus 1. And the chart then would look like this. Now notice in the chart that we have all of the elements that we had just a moment ago. We have the x approximations in this column. And so we would start here with the first approximation, and then we calculate f of x sub n, f of that x, you see, and put the value here, f prime of that same x, and put the value here. Now with these two values, we make a fraction, and we put the outcome here of that quotient. And then we take the first x, that's the x sub n at the end, and we subtract the quotient that we have here. You see, and then we make all those calculations. So if we begin over here with a 0.5 that we talked about earlier, then we just go through and fill in that first column. And notice that we go all the way across now, and this is our next x value for the next iteration. So we'll take this value and come back over and just pop it into this, this place. So enter. And this is just from over there, and we enter here, and then we fill in the next row. And then continue with taking the value at the end, putting it over here, and then again fill in the rest of the chart. And after you have filled in the chart, the way that you know that you're about finished is when you see that your x values over here that are targeting that intercept come very close together. That's one way to tell. And notice how close together these numbers are. Another way to tell is this, that in this column, now notice that this is f of some x value. Now that means that's a vertical distance. That's a y component. That's a y value. And when that y value gets really, really tiny, it means that we're very, very close to an actual x-intercept. So this value that we're using over here is certainly an extremely accurate approximation for the x-intercept or the zero of the function. Let's look at some techniques for using the graphing calculator to help us with this process. Notice I've already entered a few functions here for our consideration. The first function is the function that we started with. This is x to the 5th plus x minus 1. Now we're looking for the zero of this function, and in the chart we had a number of positions, and these other functions correspond to those other positions, and we'll get back to that in a minute. Notice that I have selected this function. This equal sign is highlighted and the others are not, so when I press graph, I can graph only the function that we're talking about here. Just want to review with you the concept of what we're dealing with here. This is our function, and we have a rather close view of it. In fact, I'll bump the window settings just to show you the x minimum, maximum, and the y minimum and maximum, just so you'll see. We have a rather magnified view of the function. Now, what we're doing is this. We're selecting a point, and we chose 0.5 as our first point, and we're thinking about a tangent line. Well, you know, the calculator is capable of drawing a tangent line at a point on a graph, and I want to show you that. It's in the Draw menu. The Draw menu is the second function on the Program button. So I'll press second, and then the Program button for the Draw menu. Item number 5 allows us to draw a tangent line. Now, we are being requested here to cursor over to the point where we want to draw the tangent line. Now, when we did our calculations on the board, we started with a position of 0.5. So I'm going to that position here, and I'm pressing enter, and now the calculator will draw the tangent line. Now, notice things get pretty tight here, because what we're saying with our Newton's method is that the zero of the tangent line, which would be this point, you see, is an approximation for the 0 of our function. And then we get a further or a closer approximation by locating the point on the function corresponding to the 0 of the tangent line. That is, we slide up here, and then we take the tangent line of that point, and then the 0 of that tangent line will get us even closer to the 0, and so forth. So that's the whole idea. That's the concept geometrically. And algebraically, then, the calculations are made according to what we have here. We start out with our function, and now we need some other information. Remember that the last column in the chart was x subscript n minus f of x of n over f prime of x of n. So that's what's being developed here. All of the parts that are in that chart that we saw earlier are right here. So this is our first function, and then this is the derivative of that function of y1 with respect to x, and for an x that will be named later. Now we're gonna choose a specific x value and store it in the calculator, and then find out what y2 is, or find out what some other items here in this display are. Now y3 is the quotient of y1 and y2, so we have the function over its derivative, which is part of what we needed, and then y4 corresponded to the information in the last column, the fifth column of that chart a few moments ago. So it's x minus this quotient, you see, which is what we had earlier. Now I want you to understand that this layout is in a rather generic form, starting with y2, that I have not re-entered the function here anywhere in the other parts. So this could be a pattern for using this system or this situation in many other functions. All we would have to do is re-enter the function in y1, and then we can use this for a lot of others. Well, here's how we're going to use it in our situation. Remember, our first approximation was an x value of 0.5. Now I'm going to clear out of this screen and go over here, and I'm going to enter 0.5 and press store, and then x, and then enter. Now in the calculator, 0.5 is the value of x. And so we can evaluate y1, y2, y3, y4. And actually it's just y4 that we want the value of, because that's the new approximation for the 0 of y1. And now to do that, we do this. We press vars, and we want a y var, or a y variable. And so I cursor to the right, and then it's a function, so I'm pressing enter. And I want item number 4. I could either press number 4 or cursor down and press enter, and then press enter again, and it will evaluate y4 for a value of 5, or excuse me, a value of 0.5 for x. Now this is now our new approximation. Now we can now take this as the new approximation and use it to evaluate y4. You see, and get a closer approximation as the 0 of the original function. Let's go through and do that. We just take this, and I'm pressing store, and it's taking the answer, the previous item, and it's storing it as x when I press x, and then enter. Now it's stored as x. And now again we'll evaluate for y4, and to do that, vars, right arrow, enter, item number 4, I'm pressing 4, enter, and here's the new approximation. Store x, enter. Vars, right arrow, enter. 4, enter. You see, now you may be recognizing some of these as values that we had on the board earlier. Again, store x, enter. Vars, right arrow, enter. 4, enter. Store x, enter. I'm just going through this several times because I want a closer approximation than we had on the board earlier. Well, let me concentrate on what I'm doing here, and I'll talk about it in just a moment. Okay, here we go. Now notice that the change from this item to the previous item. You see that the changes are now in the digits way over here to the right. So this must be a very close approximation of the zero of the original function. We could test to see that it is like this. We could store this value as x, and then we could evaluate the function. Now remember, the function is y1. So we could evaluate that y1 for the x value that we've stored like this. We could just say vars, right arrow, function, item number 1. I'm pressing enter and enter again. Now notice that this number is in scientific notation. It's an extremely tiny number, and that means that we are extremely close to the x-axis for this particular value of x plugged into our function. So for all practical purposes, this value is a 0 of our original function. It isn't terribly difficult to program a graphing calculator to perform Newton's method. And you can access on the internet, you can access sites where you can find the steps for that process regardless of what calculator you have. It needs to be a graphing calculator, but it's fairly easily accessible. You might look into that if you're interested in it. Anyway, there are two situations where Newton's method doesn't work, and it turns out that those two methods those two situations are situations in which you choose the first approximation for the intercept incorrectly. You unfortunately choose a value that, let's say, this value is chosen for x as the first approximation for that intercept, and it turns out that f of that x puts you in a position so that the derivative turns out to be 0. And if the derivative is 0, then we don't have an x-intercept for that tangent line. And in a similar way, if the graph has a kind of a turn like this, and we choose, let's say we choose an x out here, f of x is here, the tangent line is here, and the intercept for that tangent line is way over here, the x-intercept for the tangent line, f of that next x approximation puts us down here. Its tangent line is like this, and the 0 of that tangent line sends us way out here, and f of that rascal puts us up here. Its tangent line sends us in the other direction. So we're moving away from the 0. We're moving away from that x-intercept. And what we want to do is move toward it. And the idea of moving toward it, incidentally, in sort of incremental steps like this, is we can think of those succeeding x values as approximations as being a sequence of numbers. And we want that sequence to converge to the 0 of the function. And that's really what it's all about. Now we have a divergence situation in these two examples. Well, some brilliant mathematician found that you could actually make a calculation to tell if your approximation for a function is going to work, if Newton's method is going to work, if we have a convergence, that is. And here's how that works. Newton's method converges to a 0 if the absolute value of this quotient is less than 1. Now the quotient is composed of f of x, f double prime of x, that is the second derivative of x, and the first derivative of x squared. And in this situation, the x that's involved here is our first approximation. So it's what we choose that is so important here, because after all, if in either of those other two situations we had chosen a different x, then it could be that Newton's method would work. So this quotient is calculated according to a particular value of x. Let's see how this situation is calculated. Here's the function that we first talked about, x to the 5th plus x minus 1. F prime of x is this, f double prime of x is this. So we just calculate the first and second derivatives of the function. And now we use our approximation. If you recall, we used 1/2 or 0.5 for our approximation here. So we need to calculate f of 0.5, f prime of 0.5, f double prime of 0.5, and I've done that over here. F prime of 0.5 is this. We made the calculation earlier, actually. F prime of 0.5 is this. F double prime of 0.5 is 2.5. And then we just plug into that quotient. We write the quotient down. F of x for an x of 0.5 turns out to be this from up there. And then f double prime of 0.5 is 2.5. and f prime of 0.5 is this value, and it's squared in the denominator. Then we perform indicated operations. We get negative 0.68 within the absolute value symbol. Well, that's 68 hundredths, and 68 hundredths is certainly less than 1, and therefore Newton's method is going to work using 0.5 as the first approximation for x. On the other hand, here's a situation where it doesn't work, and I'm just showing you the algebra here and another way of laying this out. Y equals this function, and our approximation is 3 over 2. Well, let's see. Let's calculate y in terms of this x of 3 over 2. I've calculated it, and it turns out to be 1.5. Y prime is this, and y prime in terms of an x of 3 over 2, just replace these x's with 3 over 2 and evaluate, we get 3. Y double prime, from the y prime, from the first derivative, we can get the second derivative easily enough, and then y double prime of 3 over 2, replace the x with 3 over 2, and we get 12. You see, now with these values, with the 1.5, the 3, and the 12, we go over and we calculate this quotient. F of x was 1.5, the f double prime of x is 12, f prime of x was 3. The 3 is squared in the denominator, and performing the calculation, we find that the quotient is 2. I probably should have an absolute value symbol here. Doesn't make any difference, everything is positive. But since 2 is certainly not less than 1, this first approximation for the 0 is not going to work if we're using Newton's method. We need to choose another approximation for x.